Hi friends, in this video I'll be explaining the attention mechanism and the math behind it with an example. Before you make a API call to another transformer model or even the newer models with the mixture of expert architecture or let's just say fine tune a model or build anything with AI, you need to understand the attention mechanism. This originally came out from a 2017 research paper by Google. It was titled Attention is All You Need. A very famous paper by researchers from Google that basically changed the trajectory of AI and large language model research. And after that point, after this breakthrough, be it GPT, BERT, Claude, ChatGPT, or even the newer DeepSeek models, everything uses attention under the hood. But here's why it matters even more. Not every use case requires a massive architecture or making an API call to like a, a model with like billions of parameters or trillions of parameters. Um, and it's expensive. Once you understand the fundamentals of attention, we can just switch over to lightweight models with fewer attention heads from Hugging Face or from other service providers that can be run on edge devices, your Mac computers, or even CPUs in some cases through Olama. Um, we don't really need to call a billion parameter model with when fewer attention layers might solve our problem faster and cheaper. The good news, the math is actually beautiful. I won't lie. It's not super easy or intuitive at first, but in the next few minutes, I'm going to show you exactly how it works with concrete example. So let's get into it. Okay, so now getting into it, um, attention again. What is attention? It's basically a technique that allows large language models and specifically neural networks to focus on the most important part of an input while generating the output. Historically, large language models were processing information, and instead, I should say, deep learning networks were processing information sequence by sequence. But large language models, because of attention, they now can process long form context as well. And the technique that powers this is nothing but attention. So, where does attention happen? I'm sure all of you have heard the word transformer, which is nothing but an architecture for large language models, right? And transformer essentially has two components, the encoder and the decoder. So, attention happens in both of these blocks, both encoder and decoder block. There's a slight nuance. In the encoder block, there is multi head attention layers, and in the decoder block, there is masked multi head attention layers. Now, multi head attention layers, they do something known as self attention, wherein they have access to all the tokens. Every token has access to every other token, irrespective of whether a particular token comes before or after that particular token for which we are calculating the attention values. In the masked multi attention layers, cross attention happens, where the tokens that come after that particular token in these layers is masked. It's set to negative infinity uh, during the softmax calculation, because we don't want access to the output. So now we'll take an example and dive deep into it. So now let us take a input sentence that says best pasta in Austin, Texas, right? And what I'm trying to do over here is draw an analogy that will help us better understand um, the attention mechanism. And then I will also be introducing three key terms: Q, which is the query; K, which is keys; and V, which is values. So, so QKV, why these three things are important? Because under the hood, all of our natural language input will be converted into these three things. So either be converted or will be, or the weights will be manipulated by these three matrices. And all large language models, what they do during training is learn how to construct QKV and generate meaningful output. And the way they do that is basically by minimizing the losses, right? So coming back to the example, let's just say you went into Google Chrome right now, and then you put this in the search bar, right? So you type just the best pasta in Austin, Texas, right? What will essentially happen over here is, mm, once you search Google, it will then check this query against the keys. Google, and the key in this case will be billions and trillions of indexes of the web pages that Google has, um, right? So this will be Q, the query. And then you all know that once we put this and hit the search button, we get results, right? So we have three results. This will be basically the index with the URL, the hyperlink. This will be another URL ranked on the relevance. And then what you will also see is it has some content, which will be a summary of what's on the page, or like generally the top information of the page. To 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 continue with the example, these indexes will be the keys: k1, k2, and then the content will be the values, right? So this will be v2. And so the intuition that we need to understand for QKV, we just discussed that whatever will happen within the large language model, it will essentially be converted, the tokens will be converted into these three things: query, keys, and values. And now if you want to draw a simple um, explanation of what this is, right? So query will be, what am I looking for? Keys will be, what do I contain? And values is, what content information should I communicate to others, or what detailed information do I have, right? And this will be for each token. Each token, when we do the attention calculation, it will focus on these three things: q, k, v, right? So for each token, oops, this will be valid. Now we'll get into the math, the beauty, the actual beauty into it. Okay, so now we'll get into it, the actual math. We build the intuition. We've looked at an analogy on the QKV, right? And now I'll also introduce the actual mathematical formula. So attention of QKV is nothing but softmax, and we'll come to that. Q times K transpose on square root of the dimension of the K matrix multiplied by the weights, or in the form of V matrix, right? And we'll take a sample sentence, which is, let's just say, I love Indian food. So this is our input, and we'll compute the attention for the word Indian. This is what we're trying to do over here. This will be a 4-step process, right? And I will start with the Q of Indian. And friends, again, we have to keep in mind Q, K, V, what are they, right? Q is what am I looking for? So what is the word Indian looking for? We represent that in the form of vector. Uh, and one thing to keep in mind is, you might question, why did we take the vector size as 4, the dimension is 4? So for the purpose of easier calculation, we are here taking K as 4. In reality, if you look at the standard architectures, it's generally 512, 256, or even more than that, right? So coming back to this, we represent the word, the query vector for the word Indian, what Indian is looking for with this. Uh, we also have to do it for K. Now we will have, since we are calculating attention and attention mechanism, every word has access to every other word. So Indian will have access to I love food. India will also have access to itself, right? So we will have 4 keys to convey the information. What do I contain, right? What do I contain? So going back, so we'll start with I, and these are hypothetical vectors that I have pre-computed, but I will be doing the live calculation for the purpose of this video. So keeping it simple with 0, 1, 2, and now the last part, which is the V, right? So we are calculating the attention for the word Indian. Over here we calculated K, and now we'll also need 4 V vectors, right? Oops. Perfect. Now it's time to calculate uh, the attention, right? So in the first part, what we will do is we'll calculate this. We'll divide it by the square root of the dimensions. Take the softmax in step 3 and then multiply with the V vectors, right? So now we'll get into it, right? Step 1. So we have our values in front of us for Q times Ki. So essentially that will be 2101 times the transpose, but transpose of a single dimensional matrix with four entries will be nothing but itself. So this will come out to be 0 plus 0 into 0 plus 1 into 1. That comes up to 3. Right. We do it for Q for K love. So 2101 times K full love was 0110, and so this will come out to be 2 into 0 plus 1 into 1 plus 0 into 1 plus 0 into 1. So that comes out to be 1. Do this again for Q times K Indian with itself. 2101 dot product 2101, right? And this will come out to be 2 into 2 plus 1 into 1 plus 1 into 1. That comes out to 6. And then Q times for the last one, food. This comes out to be 4. Okay, so now what we've done is we have calculated this part. Now we will. This is pretty straightforward in step 2. So we've taken a sample value of 4. It will be basically square root of 4. It comes out to be 2, right? So our vector will be nothing but 3 1. So 3 1 6 and 4, right? 3 1 6 and 4. That's basically our Q K transpose. Square root of D is 2. So now we'll end up dividing this, right, to get 1.5, 0.5, 3 and 2. And now we have to apply softmax, right? Now softmax, right? So step 3, softmax. So what softmax does is it converts these scores into probabilities where the sum of these probabilities will be 1, right? um, and the reason we do this is we need to normalize these um, in order to keep the values in a certain range and avoid the problem of vanishing gradients, right? So softmax formula is basically e to the power xi upon sum of e xj, right? So essentially we will calculate each of these values and then normalize it with the sum, right? So I've pre-computed. So this will be e to the power 1.5, e to the power 0.5, e to the power 3, the power 2, and this will come out to be 4.48. This will be 1.65, 20.09, 7.39, and the sum, if we add everything, this will be 27, 31, and it will be 33.61. So now we will normalize this, right? So essentially what it would become is 4.48 by 33.61, 1.65 by 33.61, and then the last one. So if we do quick rough calculation, I'm doing on here on the side, so this is okay. So now we have completed up to step 3, which is we did this, we've taken the softmax. Now only the last part is remaining, but friends, this is where we build the intuition, right? So now we have the the attention weights with us, right? And this is basically softmax qk transpose by square root of d till this point, right? And so now this is for I love Indian food. So now this gives us this built-in intuition, right? This says that the word Indian should pay 60% of the attention to itself, 22% attention to food, to the word food, 13% attention to the word I, and then 5% to the word love, right? So attention, right? Self attention. Every word has access to every other word, right? Before, irrespective of it, whether it comes before or after. So now this actually this is how it's making the semantic sense, right? When we try to understand like the word Indian and how much should the model focus on most of the words, right? During the attention phase. So now, coming to step 4, which is the last phase, and we will now use these attention weights to combine with the value vectors, right? The v part is still pending. So we had declared 4 v vectors over here, and we will be multiplying it. And so the way we will be doing it is this will be a component wise calculation, right? Step 4, component wise calculation, right? And so for each position, we will be basically calculating a weighted combination of these weights, right? So that will come out to be 0.13 into vi plus 0.05 into v love, because these are the attention scores, normalized attention scores, right? 0.60 into v Indian plus 0.22 into v food, right? And the way we will be doing it is we go back. So on the first position, right? Since this is a component wise calculation that depends on the position, so it's the 1203. So for position 1 will be 13 into 1 plus 0.05 into 2 plus 0.60 into 0 plus 0.22 into 3, right? Position 2, this will be 0312, so it will be and so let us quickly calculate these two. This is coming out to be 0.89, this is coming out to be 1.19. Position 3, we go and check, it will be 2031. 2031 is what we have to multiply. Again, the point to remember over here is this is a component wise weight calculation. And so this will come out to be 0.26 plus 1.80 plus 0.28, and then the last position, that is position 4, is basically 1120. So 0.13 into 1 plus 0.05 into 1 plus 2 plus 0.22 into 0. So this comes out to be 0.13 plus 0.05 plus 1.2 plus 0. Okay, so now the attention output for the word Indian, right? That comes out to be 0.89, 1.19, 2.28, and 1.38, right? And so how do we interpret this, right? So this we calculated until step 3, we calculated the q and k, right? And then we basically mixed information from relevant words, right? And through the v, and then the final output is like the actual enhanced representation of Indian, uh, that includes uh, the context from every other word, right? And so this is basically our um, final output. We performed 4 steps calculation to come to the attention values, right? So these weights will give you an idea as to like how much a word should actually focus on the other words uh, that are present. So I hope this gives you an understanding of like exactly what happens in attention with the calculations. All right, so now that we have the final attention output, we'll just quickly uh, list down the key takeaways, right? So what are the key takeaways of this representation? Each dimension, right? Each dimension captures some uh, abstract meaning behind it, right? So this, let's say this 0.89, this has captured the meaning for the word Indian, right? 1.19 has done the same, and the values basically encode how strongly that feature is present, right? And the combination of this contextualize and understanding uh, of the word Indian specifically in the phrase "I love Indian food" is uh, is what is being represented over here, right? To end uh, our video, I'd like to end with the bigger picture, right? So we discussed attention, we looked at an example, and I'm sure all of you have seen this diagram, which is the encoder block and the decoder block over here, right? And so where actually does the attention happen? Say attention happens in both the blocks, right? And it happens for every word, um, while looking for every other word in the sentence. And this is just single head attention, right? In the image you see multi-head attention, the mass multi-head attention. There are multiple heads that focus on capturing different relationships between the words, right? So you have one head that can focus on adjectives, the other head can focus on the grammar, there can be another one that focus on the semantic meaning, and based on, and that's what contributes to the actual number of parameters and the size, and then the hardware requirements for building a large language model, right? So there it is. That's the attention mechanism. Again, it isn't magic, it's just pure math. And in the understanding of QKV, the dot product and Softmax is basically the core of how attention works, right? So I hope you like this video, and thanks for it, friends.